Scott's Nerd here, back with another one. All right, so those of you working in my AP class, you've been dealing with a problem involving two masses. One mass sliding down a ramp and over there. Now, I just finished recording the Atwood device video, and the Atwood device video you're gonna find is it's gonna be the exact same situation, except we're gonna have to be worrying about this angle, theta here. All right, so let's just make a base formula. Good trick to do in physics before we plug any numbers in. Okay, let's follow the logic. Okay, let's pretend as though this is falling that way, this is going that way. Now if it was going the opposite way, everything would still work the same. Yeah, everything that's opposite would still remain opposite. And if you plugged in all the values, we get the same answer. But let's start with mass 1. So, the sum of the forces, I must have made a big mistake there. We want a free body diagram first. So, free body diagram for mass 1. I'll put M1 right here. Okay, we have the tension force. That's this line right here. So, I'll put T. Okay, and we have the force of gravity pointing down. Okay, once again, I write out the forces for the free body diagram before I ever think about breaking them down in their components. Okay, I know it seems a little tedious, but that's what they look for on the AP exam, so that's what we're going to do. All right, let's write it out. Sum of the forces for mass 1 is equal to, which is a little thing here, is equal to tension plus the force of gravity. And we know that's going to be equal to the mass 1 times some acceleration. We'll call that acceleration 1 for right now. Now, if you noticed, I added these together even though they're opposite directions. Once again, I told you this on the last video. If you're in my class, you've heard me say this 100 times. If these are opposites in forces, but when we plug in the values, they're going to become opposite automatically. We don't want to end up with a double negative because we assumed the answer was opposite and then ended up with another negative here. We want to add vectors together. So we're going to keep everything as an addition until we plug in values. All right, so I'm going to rewrite this down here as the sum of its parts. So force of gravity is M1G equals M1A1. And we're pretty much done with that one. There's no angles involved, nothing else. At some point I am going to solve for t because we're going to want to do a system of equations for the second part like we did in the last one. We're not going to do that yet. All right, now let's focus on mass 2. All right, well, free body diagram for M2. There's the tension up, so I'm going to go tension this way, force of tension on mass 2, and then we're going to have the force of gravity down this way. Now, by the way, this is T. This tension on the first situation is equal to the tension in the second situation because we're assuming first that the line is massless. Okay, once again, remember that's the reason we do that is you can imagine as more string fell over the edge, this side would get more massive and therefore there would be a problem with changing tension or changing mass. We don't want that. It's for calculus. Because anything that's changing a lot involves some calculus. Anyway, so this is going up, that's going down. Okay, this is the tension vector, this is the force vector. Okay, you can already see why this is a different sort of problem, right? Well, let's sum our forces. We know that the tension, we know the tension plus the mass times gravity, M1G, is going to be equal to, as you were, M2G, is going to be equal to the mass of 2 times the negative of acceleration 1. This is very similar. And the reason I'm saying this is I could have said A2, but we know that these accelerations are the same for both boxes, but one is going in the opposite direction as the other. So we need to actually identify that here. And to make our lives easier, I'm going to multiply out that negative right at the beginning here and put it in the front of the whole thing. So we got negative M2 A1. All right, we're missing something here. Because we're dealing with an angle on a ramp, yeah, gravity's pointing down like that, right? But the portion of gravity that's affecting us, now we are pretending this is a frictionless surface, that does simplify things, but the part of gravity that's affecting us is really just a chunk of it, right? Because some of it's being lost to this contact force with the surface. And by the way, the contact force with the surface points in that direction. Okay, but to be a proper vector, so if you guys know about vector addition, if we add this arrow, the normal force, the arrow pointing down, to that arrow, we should get the gravitational arrow pointing downwards. So if you notice, I sort of made a right 90-degree angle, but it's turned upside down and sideways. So that has some interesting consequences. One of those consequences is this ends up being our x-axis, and this ends up being our y-axis, up and down this ramp. I know it seems a little confusing, but that's what's going on here. Now, of course, we're moving that way, so our y-axis might go up that way. That might be the negative. That'll be positive. But one of the things that happens because of this new orientation, remember I said in physics, we make up our own coordinate systems. Just as long as they stick to the whole time, we're fine. But one of the consequences of that is, if I want to know how much of my gravity is in this direction, it is no longer the cosine, because we're not in the horizontal. The y means that we're going to be using a sine of this angle to find that force. So instead of just m2 times g, it's m2 times g times the sine of theta. Now, what's interesting about sines and cosines, if you don't know this already, is they act almost like they always shrink your value, right? This is going to be some decimal, and it sort of makes sense. It's going to reduce this force to only the part of it that's in our direction. So we shouldn't get we should never get m times g unless we're pointed straight down. Because we're pointed a little off, this number is going to be some decimal that's going to reduce this total. And that it should. If you get an answer where this is like a number bigger than 1, this sine of theta, or it makes this number larger, we've messed up somewhere in the math then. It should always make it smaller. Okay, unless of course it's 100% in the sine direction, which is downwards. All right, so t plus m2g sine of theta equals m2a1. By the way, it's negative m2a1 because down versus up. All right, now let's box this in. And what we're going to do is we're going to solve for t in this one. So t equals m1 a1 minus m1g. So all I did was move this over there for the first situation. And now I'm going to plug all of this in for t. So we end up with m1 a1 minus m1g plus m2g sine of theta. Okay, this is seeming like it's really long, right? Equals negative m2 a1. And then I'm going to, just like we did in our previous problems, I'm going to get all the a1s, everything with acceleration in it, and everything with gravity in it on opposite sides of the formula. So I'm going to move, let's see how I'm going to do this. Let's move this over here first. So we end up with m1 plus m2, and that's a1 equals, well, let's move all this over, equals m1g, because I made this positive when I moved it over, minus, because this becomes negative when I move it over, m2g sine of theta. All right, so now things are separated. Now, like in the previous problems, like with the Atwood device, I'm going to pull g out front in here, and I'm going to pull a1 out front here. I'm going to write this in a different color so it stands out a bit. We're going to get a1 times m1 plus m2 equals, I'm going to pull g out front, g times m1 minus m2 times the sine of theta. And once again, like in the previous problem, we're going to move all of this into there because remember what we're solving for. We're trying to find the acceleration, which is nice because that'll tell us how fast that's going up and how fast that's dropping. So we're going to end up dividing that over here, dividing this entire bracketed thing under there, because remember, to undo multiplication, we have to do division. m1 plus m2, going to get rid of all that and leave the a1 right there. And I'm going to box this in as sort of our finale here. That is the formula. I'm going to take the camera here real quick. That's my son, if you saw him on there, helping me out. Okay, there's the formula for that situation. Okay, well, going back to the Atwood device, there's the formula for a a situation involving just a box, a pulley, and another box. And then here's the situation for a cart being pulled by a falling pulley. Okay, that's the cart pulley. That's the traditional Atwood device pulley. And this is the sliding block on the platform formula. And if you notice, they're all basically the same formula. We're just adding pieces as we go. Now, we're not going to do this, but could you imagine if there was if on the other side there was also an angle and the box was sliding up the ramp? Well, all we would do is we deal with the sine, or it would be the sine again, the sine of the angle with this, because it would be opposing that one, and it wouldn't be all of G, it'd be a portion of it. So this gets really fascinating, is you can pretty much do any scenario now involving sliding blocks using the idea of the base formula we started with. If you have any questions, leave comments below, or send me a message or email me if you're one of my students. But hopefully that simplifies things a bit for you, that if you use free body diagrams, sum of the forces, and then find a common variable that you can solve for, you can get to a solution. And once again, another thing that's amazing about this is we could have a box sliding up a ramp and falling on the other side, and guess what? We don't need to take any measurements except for the angle and the masses to find the acceleration. Like I said, that's the beauty of the Atwood device. What else was I going to say? You may see a problem like this where it says solve for the acceleration and then find the tension, right? Find the tension. Well, that's pretty easy to do. Once you find acceleration, you're just going to plug it back into the original formula right here. Acceleration, mass 1, gravity, and solve for t. That's like a two-step problem. Anyway, there you go. Scott's a nerd. That's physics.